class, let's do some more linear algebra. Today we're going to focus on the determinants of type 2 elementary matrices. Generally speaking, a type 3 elementary matrix adds alpha times row I to row j, where alpha is some non-zero real number. Generally speaking, they look like this. They've got ones down the diagonal, but there's going to be an alpha somewhere. And that alpha, the position of that alpha depends on what E3 is trying to do. If this E3 adds alpha times row I to row j, the alpha is going to be in row j and in column I. Zeros everywhere else. As with the other elementary matrices, we are concerned with the determinant. Claim 17. If E3 is an n by n matrix, an elementary matrix in particular of type 3, which adds alpha times row I to row j, and A is some other n by n matrix, then the determinant of E3 times A is precisely the determinant of A. We're going to need several steps to prove this. The first thing that we need is a lemma. This lemma is not going to look like it's related, but bear with me. If A happens to be an n by n matrix, remember the notation for cofactors. Aij, where I and j are some integers, is the cofactor corresponding to the entry little aij in A. Let's examine a sum, aik, big A, jk, as k goes from 1 to n. Let's expand this so that we can discuss what's going on. Little aij times, this would be little ai1 times cofactor aj1 plus little ai2 cofactor aj2 plus dot 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 ain ajn. This looks very, very similar to a normal cofactor expansion from the determinant. Here are your coefficients, as if you were taking the cofactor expansion along row I to find the determinant. But the cofactors are the cofactors as if you were going down row j, and I and j might not be the same. This lemma claims that this sum is going to be the determinant of A when I is equal to j, as you would expect, and 0 when I is not equal to j. Before we prove this, let's walk through the idea of the proof. Idea. I'm going to introduce something called A star. This is the matrix obtained from A by replacing row j with row I. So as an example, take a look at this. If A is going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, and I is 1, and j is 3, then A star is going to be 1, 2, 3, 4, 5, 6. Then we replace row 3 with row 1. 1, 2, 3. Let's find the determinant using the jth row. And let's see what happens. If I'm finding the determinant of A, using the third row, I would start here and ignore the row and column that 7 is in, and then I would multiply by plus or minus the determinant of the matrix that's left, this being M31 in A. If I were to do the same thing in A star, I would start with the determinant by starting with 1, erasing the row and the column that it's in, and then multiplying by plus or minus the determinant of the matrix that's left. This is M31 in A star. And you'll notice that M31A is equal to M31A star. Same thing for M32 and M33. So let's talk about this determinant. The determinant of A star is going to be 0. That's because 2 rows are the same and claim 13. But we can also come up with an expression for it. It's going to be 1 times the determinant of this matrix, 2, 3, 5, 6. It's going to be minus 2 times the determinant of 1, 3, 4, 6, plus 3 times the determinant of 1, 2, 4, 3. And this is going to be, notice, this is A11 in A times A31 of A star minus A12 in A times A32 in A star plus A13 in A times A33 in A star. But as we pointed out before, the cofactors are the same in A and A star when we're moving along row J. So this is A11, A31 in A minus A12, A32 plus A13, A33. And here we've proved that this expression, when we're taking coefficients along row 1, but cofactors along row 3, is going to give us 0. This is the idea. Now let's prove it. Lemma 16. If A is an n by n matrix, and Aij is the cofactor for Aij, little aij, then the sum of Aik, big A, jk, for k equals 1 to n, is equal to the determinant of A when I is j and 0 when I is not j. Proof. When I is equal to j, this is the cofactor expansion for the determinant of A along row I. Thus, it's just the determinant. When I is not equal to j, then we're going to introduce this tool, A star. This is the matrix obtained from A by replacing row j by row I. We're going to do the cofactor expansion of the determinant of A star along row j. And here's what we're going to get. The determinant of A star is 0. Why? By claim 13, because A star has 2 rows that are exactly the same. This is the sum of Aik, Ajk in A star, k equals 1 to n. And since the cofactors are the same, This is AIK, AJK, k is equal 1 to n. End of proof, QED. All right, but what were we trying to do? Question, what happens when we multiply by a type 3 matrix? And does it change the determinant? For this, I just want you to recall that when we add alpha times row I to row j, where A is the matrix Aij, then what we get is a matrix that looks like this. In the ith row, we're going to just have what we have. In the jth row, it's going to be alpha times AI1 this of course being 1 plus AJ1 dot 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 all the way over to alpha AIN plus AJN. This of course is the matrix times A. Nothing else changes. And in particular, MJK in A is going to be MJK in E3 times A for all K. Now let's prove claim 17. If E3 is an n by n elementary matrix of type 3 that adds alpha times row I to row j, if A is an n by n matrix, then the determinant of E3A is equal to the determinant of A. In straightforward language, replacing a row with its sum with a scalar multiple of another row does not change the determinant. In particular, as a consequence of that, the determinant of any such type 3 matrix is 1. Let's prove this. Proof. We're going to expand the determinant of E3A along the jth row. The determinant of E3A is, of course, alpha AI1 plus AJ1 times this cofactor, alpha AIN plus AJN times this cofactor. This is coming from what we know about E3 times A. Let's just use our sum notation and gather like terms. So we're going to gather all the terms that have alpha together. So we're going to have this aik, ajk, k equal 1 to n, and we're going to gather all the terms without an alpha. Ajk, big Ajk, k equal 1 to n. This is 0 by Lemma 16. What's left is this sum. Which of course is the determinant of A using the cofactor expansion along row J. Using what we just learned, we're going to apply it to the case where A is equal to the identity matrix. This allows us to say that the determinant of E3 is equal to the determinant of E3 times I. Using what we just proved, this is equal to the determinant of the identity matrix, which of course is 1. QED. End of proof. Let's do an example. Example. Let's look at the matrix A is equal to 1, 2, 3, 4, 5, 6, 0, 0, 0. We want to find the determinant of A. Of course, I could find it directly, and it would be 0. Now let's look at B. 1, 2, 3, 4, 5, 6, 2, 4, 6. And we want to find the determinant of B. Notice that B is the matrix where we added 2 times row 1 to row 3. This is A, but we've added 2 times row 1 to row 3. By the claim, this means that the determinant of B is equal to the determinant of A, which is 0. Here are some lingering questions I expect you to have. How does this help us? In particular, how does it help us show that the determinant of A is equal to 0 if and only if A is singular? I did say a few videos back that this was our goal. We'll be able to do this next. And another lingering question could be, is there a geometric interpretation for both determinants and the actions of elementary matrices, both in what they do to another matrix and in what they do to the determinant of another matrix? The answer to this is yes. We will also be doing that soon. But for now, think on this. We'll see you next time.